environmental tracer for salinity origin in groundwater samples in Pampanga, Philippines. We have two presenters today. Dr. Angel Bautista, a senior science research specialist of the DOST Philippine Nuclear Research Institute, and Dr. Sunshine Tan, Geotechnical and Environmental Engineering Program of UP Diliman. Before I could continue this, and we would like to ask Dr. Decibel Eslava, the Dean of School of Environmental Science and Management, to give us an opening remark.
Good afternoon, everyone. Thank you for making time to attend this webinar. So, as mentioned, we have two speakers on the topic that was mentioned. I would like to thank you for making time to be here online with us. And of course, I thank Dr. Angel and Dr. Sunshine for preparing the talks on such a short notice. Maraming salamat. Living Dangerously is a seminar series that SESAM started to organize this year. We noticed that 2020 we started on some very weird events happening. So we thought, let's come up with a platform for discussions. And the Living Dangerously seminar started with a talk on COVID this year when it was just when the issue was just erupting, and we had some kind of disease epidemiology modeling studies. And the second paper was on water shortages, water management, because we were seeing that this summer, again, the problem last year that Metro Manila with our experience might be something that was in the offing, and we're heading that way. And the third talk was on volcanic eruption and we were supposed to have a talk on biosafety, particularly on ASF, and because ECQ was closed, we had to postpone the talk. So today, we're very grateful to Dr. Sunshine for preparing their materials to share with you today. And but already I would like to invite you for the next talk on May 29 on ASF, which will be delivered by Dr. So with that, I hope we have a very productive afternoon.
Thank you very much, Doc Day, for that welcoming remarks. So for our two presenters today, we will have first Dr. Angel Bautista from the Philippine Nuclear Research Institute, DOST. He graduated Ph.D. in Nuclear Engineering and Management, University of Tokyo in Japan, Master's degree in Environmental Science in UP Diliman, and a Bachelor of Science in Chemistry, UP Diliman also. His research interest is protection of environment and general public through environmental food research using nuclear and isotope-based analytical techniques. One of his research programs include the screening for radionuclide contamination from the Fukushima accident by iodine-129 measurement in corals from the Philippines. Also is the detection of the adulteration of Philippine honey using carbon-13 isotope analysis. That was funded by DOST Pesur. So Dr. Angel, if you're ready, can you start your presentation right now?
So, good afternoon, everyone. Thank you very much for the kind introduction. So again, I am Angel. I'm from the Philippine Nuclear Research Institute. So first, I want to say my gratitude to UPLB SESAM, to the whole team, to the invitation of Dean Day for giving us this platform, for lending us their platform to share with you our work today, which is about Okay, so about IDIN 129, how we use IDIN 129 to determine the origin of salinity in groundwater in Pampanga, Philippines. So this work is actually the dissertation of Dr. Sunshine Tan, which will be speaking after me, who will be speaking after me. So I will give the first part of the presentation and then followed by Dr. Tan. So I was her co-advisor together with Dr. Ogie Resurrection of the Environmental Engineering Program of UP Diliman. So this work was a collaboration between PNRI, between UP, but also with DNR Mines and Geosciences Bureau. So Sunshine did her sampling with MGB. And of course, we would not be able to do this without the help of Professor Hiroyuki Matsuzaki from the University of Tokyo, from our lab in Japan. So before I go into the presentation, I would like to share happily that we just published this work that which will be presenting to you today um, in the Journal of Environmental Radioactivity. So if you're interested for a copy, you could email Sunshine and her email is flashed there. Another thing I would like to share is that we shared this study last year in the International Conference of Environmental Radioactivity in Prague last September 2019, and we're happy to say that it won the first place in the oral presentation category. So we're happy to share that. So, okay, so let's go now to the presentation. So I will be giving the introduction part, and then Sunshine will take the stage after me. So first, the background and the significance of the study. So we think this study is very timely, especially for the Philippines or in Metro Manila today. We've been having this water shortages and water issues. So the National Water Resources Board actually uh, identified Pampanga province as one of the critical areas in terms of water resources. One of the issues is diminishing groundwater quality, particularly salinity. As said in one of the reports of MGD in 2011, it was noted to be saltwater intrusion. So we want to assess the groundwater vulnerability with regards to salinity in order to meet the increasing demand for fresh water for all of us. Just to share about the study site, especially I think we have some people from outside the Philippines. So Pampanga is a province about 1 to 2 hours drive north of Metro Manila. It's in the central Luzon area, and at the southern part is located, Manila Bay is located. So any saltwater intrusion could probably come from Manila Bay. Um, some possible sources of salinity that we are looking at. Of course, one is saltwater intrusion, probably from over pumping of groundwater. Or another thing is there's very extensive river channels through Pampanga going from the central Luzon down to Manila Bay. So there may be also some tidal incursion from Manila Bay going up the river. So that's another way of saltwater intrusion. The second possible source of salinity we're looking at is brine fossil water or trapped old marine water. So what is this? So I'm not a geologist, I'm actually a chemist, but they say that Pampanga, the geology of Pampanga is alluvial or alluvium. And there are a lot of deposits, sediment deposits that actually form the Pampanga province. So it's because, again, of the extensive river systems. So there may be a possibility that historically some of the old marine water got trapped through this sediment movement processes. And I think this has been seen before by georesistivity studies by MGB as well, I think. So this brine fossil water has been seen before as well. So that's the second source of salinity we are looking at. The third one is non-marine origin, totally not coming from the sea. What are these possible sources of salinity? It could be natural weathering of our rocks, for example. That the other thing is evaporation. So again, there's a lot of rivers. There may be farms. So if water is given enough time to evaporate before it infiltrates the ground, there's a chance that the amount of water will decrease and the concentration of the salinity will increase. So that's another cause for a non-marine origin, possible source of salinity. And the third one is wastewater. If there are anthropogenic activities or man-made activities happening throughout the province, and those activities, some of the effluents seep into the groundwater, that could also cause an increase in the salinity. So these are the possible causes we're looking at, but the question we're trying to answer is how do we know from which source is the salinity actually coming from? So salt is salt. I mean, sodium is sodium, chloride is chloride, iodine is iodine. So if it's the same, if we're just looking at the chemical identity of the salinity, it may be quite hard to determine from which it is really coming from. But in this study, we're not only looking at the chemical identity of the salinity, we're also now looking at the isotopic uh, identity of the salinity, the isotopes within the salinity. So our general objective in this study is we want to identify, or we want to try to identify the origin or the sources of salinity in the groundwater in Pampanga using iodine 129 and iodine 127. So let me explain further about iodine 129 and iodine 127. Both of these are iodine. So they are both iodine, meaning they have the same number of protons in their nucleus, but the difference lies in the number of neutrons in their nucleus. So they're actually isotopes of each other. So iodine 129 has more neutrons in its nucleus, and it's a bit heavier than iodine 127. So the atomic mass unit of iodine 129 is about 129, and the atomic mass unit of iodine 127 is around 127. So iodine 127 is the most common form of iodine. It's stable. It's the most abundant. And then, but a very small fraction of iodine in the environment is actually iodine 129. And we're gonna look at the differences between that two, and I'm gonna explain further in a bit. So using iodine 129 and iodine 127 isotopes, we wanted to compare it with the more classical parameters we use when we look at groundwater. For example, we also look at the major ions in groundwater, the cations, sodium, potassium, magnesium, calcium, or the anions like chloride, sulfate, or bicarbonate. So we looked at in conjunction with iodine 129 and 127. We also looked at another type of isotopes, but these are stable water isotopes. They are H1, that's the most common form of hydrogen, and we're looking at them in conjunction with H2, that's the heavier form of the hydrogen. Not so common, but it's there. It's deuterium. We're also looking at oxygen 16, the most common form of oxygen, versus the heavier isotope of oxygen, oxygen 18. So we're looking at these three groups of parameters. The ions in groundwater and the stable water isotopes are the more um, established parameters when we're talking about hydrology. But now we're trying to see what iodine 129 and iodine 127 can put into the table together with these two groups of parameters. So that's our objective for this study. Um, So let me talk more about iodine 129. So again, iodine 129 is an isotope of iodine. It is actually radioactive, but it's not too harmful because its half-life is very long. Its half-life is 16 million years. So it's almost stable, but still not. So it's still radioactive. So it is produced naturally in the environment. And I'm sure shown here in the screen is actually the chemistry of iodine in the environment. Compared to other elements, it's somehow easier to track. It's easier to understand the chemistry. It's how it moves through the environment. And so we say it's a conservative tracer across the environment. So back to the source, again, it's produced naturally in the environment. It's produced by cosmic ray reactions in the atmosphere. So because it's produced by cosmic ray reactions in the atmosphere, we say that it is a cosmogenic radionuclide. Another natural source of iodine 129 is in the crust. So it can be produced if you have uranium in your crust and it's spontaneously undergoing fission. you can also produce iodine-129 because iodine-129 is a fission product. So, but the amount, so it's produced naturally, but the amount of iodine-129 in the environment produced naturally is so small compared to the amount of iodine-129 produced by human nuclear activities. So, from year 1950 onwards, we call it the nuclear age or the advent of the nuclear era. Mankind started to do different kinds of nuclear activities. This includes nuclear weapons testings in the 1950s to the 1960s. We have nuclear fuel reprocessing, and we have nuclear accidents like the Chernobyl accident or the Fukushima accident. So all these activities actually contribute iodine-129 into the environment, and the amount these activities contribute are so big compared to the natural levels. And how big? So the natural levels of iodine-129, we look at the levels of iodine-129 in terms of ratio. So the amount of iodine-129 divided by the amount of the stable iodine-127. So the amount of natural iodine-129 is only has a ratio of about 10 to 13 to the 10 to the negative 14. So imagine one in the environment, one atom of iodine-129 versus 10 to the 14 or 10 to the 13 atoms of iodine-127. That's how few iodine-129 is in the environment. But again, with the advent of nuclear era, the nuclear age, we put a lot of iodine-129 into the environment. Those levels increased to a ratio to about even to about 10 to the negative 6. So that's about 6 or 7 or 8 orders of magnitude above the natural levels. So that's what we're looking at. So using that property of iodine-129 in the environment, that's what we want to exploit in this study. Because iodine-129, its orders of magnitude difference in the different parts of the environment, we can use it to trace the different processes in the environment. For example, if the sample is very old, if it was before 1950, so we expect that its iodine ratio is about 10 to the negative 13 to the 10 to the negative 14. But if the sample is new and it's after 1950, then the ratio would be very different. So for example, in rain, the ratio is about 10 to the negative 9. In ocean, the ratio is about 10 to the negative 11. It's also very different in the rivers, different in the groundwater. So all these different bodies of waters have different ratios, orders of magnitude. So using that principle, that is what we want to exploit and use when we trace the groundwater salinity in Pampanga. So yeah, so that's my part of the presentation. So I would like to give the floor now to Dr. Sunshine Tan to give the rest of the presentation.
So for the information of our participants, Dr. Tan is a graduate of Ph.D. in Environmental Engineering at UP Diliman, and she finished her master's in Geotechnical Engineering at the University of Tokyo. She was a scholar of the ERDT Department of Science and Technology Program, GSRGP of the Philippine Nuclear Research Institute and the Japanese government. Last September 2019, she presented her dissertation at the 5th International Conference of Environmental Radioactivity in Prague, Czech Republic. She won the Best Oral Presentation. She currently is practicing the geotechnical and environmental engineering in various projects such as the North-South Commuter Railway and MRT-7. Let's give the floor to Dr. Tan.
So thank you po. Thank you for the introduction. So good afternoon, everyone. I am Sunshine Tan, and I'll be continuing the presentation of Doc Angel. So I believe we have international participants as well. So our presentation will be in English. So continuing what he said, Doc Angel. So we have now a brief background of what iodine-129 is and what iodine-127 is. So we did our sampling in 104 locations in Pampanga. So you can see the dots here. And as Doc Angel said, Manila Bay is down south from Pampanga, from the boundary of Pampanga, and the rest of the perimeter is land. Okay. And so we did our sampling on July 2017, which is a rainy season. And the samples were taken in various production wells in Pampanga from different water companies. So a production well is mainly used for commercial utilization. That's basically where our tap water comes from if your service provider gets their waters from groundwater. And we also sampled shallow groundwater. So this is what it looks like. So we had our measurements in the University of Tokyo. So the iodine 129 and iodine 127 ratio was measured using the AMS, or the accelerator mass spectrometry, and the ICP-MS measured iodine 127. So multiplying the two, if you multiply the ratio and iodine 127, then you would yield the value of iodine 129. So this is what the AMS looks like, the facility in the University of Tokyo looks like. So you place the sample in the top floor here, and it's accelerated down to the first floor, and the iodine ratio is measured here in the basement or the ground floor of the facility. And this is what the ICP-MS looks like. So now we proceed to the data and analysis. So this is where the exciting part comes in. So first, this slide shows the results of the hydrogeochemical analysis. So traditionally, if we talk about salinity in groundwater, what we check is the Cl content. So we used the Simpson ionic ratio, which is Cl over HCO3 ratio. And generally, a high Cl would indicate marine origin, while an HCO3 is naturally terrestrial. So Simpson ionic ratio says that if you have samples higher than 0.5, then it would indicate that the samples would have salinity from seawater or marine origin. So out of the 104 samples, we found out that there are actually 9 samples that have marine origin. However, some data locations are relatively far from Manila Bay, indicating that there may be other sources of salinity. So as we can, I don't know if you can see my pointer, but if you can see, this is Manila Bay down south, and you see that the interested points are actually far from Manila Bay. And then we use what we call stable water isotopes. So this slide shows that stable water isotopes of the 9 samples. So if the samples are from seawater origin, basically the graph would tell you that if the data should lie along the seawater mixing line, so along the red dotted line. So ideally, if all your samples are mixed with seawater, we should expect that the data should lie on the red dotted line. However, as we can see, it does not lie. So we cannot confirm the origin of salinity is from the sea using this graph. So we need to further investigate using iodine 129 and iodine 127 in the next slides. Okay. So using iodine 129 and 127, we actually compared or made two graphs to understand the salinity origin in groundwater. So these graphs are iodine 129 versus chloride, and iodine 129 over 127 ratio versus 1 over iodine 127. Okay, so this is the first comparison that we made to understand the origin of salinity. So the basic idea is if you have low iodine 129, it means that there's no exposure to man-made iodine 129. And if you have high iodine 129 content, then it means you have high exposure from man-made sources. And so that's where the y-axis comes from. And when you see the x-axis, which is chloride, a higher chloride concentration generally means that it's nearer to seawater signature. So based from that idea, we come up with the idea that groundwater from rainfall origin should have low chloride concentration with low iodine 129 concentration because it's far from man-made sources, ideally. And you have evaporated water coming from rivers or lakes or surface water in origin, which has higher chloride concentration than fresh groundwater. And it should have, well, depending on exposure, the iodine 129 would slightly increase or decrease. And now also we have seawater, which as we know has high chloride content. And we expect it to have high iodine 129 concentration due to the more exposure of the seawater to iodine 129 man-made sources. So it's very exposed to man-made iodine 129. That's why it has high iodine 129 concentration. And we also expect brine fossil water, which is trapped seawater due to deposition of sediments. It should reflect to have high chloride since it came from marine origin. And it should have low iodine 129 because ideally it's not exposed to iodine 129 man-made sources. And we surmise that the mixing of the groundwater to seawater should be in this line. So if you have data points between this, it should be an indicator that seawater is mixing with your groundwater. And of course, we have rainwater over here that has high iodine 129 content and with very low chloride concentration. And consequently, we can have the sense of age of your water sample because if you think about it, if you have higher concentration of iodine 129, then it means that it's likely younger because it's more exposed to man-made sources. While if you have lower iodine 129 concentration, then you have an idea that it could be older groundwater because it's not exposed to man-made sources. Okay, so this is the results of all our data points. And we can see that using the iodine 129 versus chloride graph, the data shows a clear distinction from rainfall recharge, evaporated water, and brine fossil water. So brine fossil water is expected to have a high signature of high chloride and low iodine 129. And the data LOB01 is seen to be the only groundwater sample to mix with brine fossil water. And in this graph, we could see it's notable that MBP 27 is seen to have a distinct signature among all the groundwater samples clustered as evaporative water. Based on its location, we checked that it's near an egg farm. So we checked where we sampled MVP27, and it was a shallow well. And we established that salinity is likely to be from wastewater from the egg farm. And interestingly, there are no samples indicating seawater origin because we don't see any distinct distinct sample that could possibly be in between the rainfall recharge and the seawater signature. So it indicates that salinity is generally from evaporative sources, as these samples are located near commercial fish ponds or river. And so by using this graph, we have distinguished the origin of salinity from our groundwater samples. And a conceptual model summarizing the iodine 129 versus chloride graph is shown here. So what I've just mentioned a while ago describing the iodine versus chloride graph is seen here. So you can also refer this graph in our journal article that we can freely give to you upon request. And so we also have another graph that we made. So lastly, we propose a graph to depict the origin of groundwater by its interaction from various recharge sources. So we compiled ranges of different sources and its iodine 129 and iodine 127 values. So for example, we have accident affected rain here. So this is the values taken from the recent Fukushima accident. And then we have values of modern rain. We also have fossil rain, old rainwater. And we also have surface seawater and deep seawater. I think the deep seawater was taken 500 meters below the surface seawater. And we also have natural brine or salt domes naturally occurring. And we also have natural rock. So the basic idea here is we also connect the data points with lines signifying the mixing of each member. So this is what we did. And now we plot the data that that was mentioned that could possibly have seawater contamination. And we could actually see that these data lie on the line where the surface seawater and deep seawater interacted. So it's actually far from rainfall origin. But however, we can see here that there's actually no distinction between evaporated water and seawater mixing origin. So unlike in the previous graph where we can actually say that this salinity may probably come from seawater. So here we can just see that, like the other graph, we can see here that LOB01 is distinctly near or similar to the signature of deep sea water, wherein we actually said that it's probably from brine fossil water. All right, so using those two graphs, we can now conclude that the objective of the study has demonstrated, the research demonstrated the use of iodine 129 and 127 isotopes by integrating it with hydrogeochemical and stable water isotopes parameters. And the location also provided key information on the origin and mechanism of multiple salinity sources. So the concluding findings further provide a basis for zoning and regulation, policy making of government and private institutions. So I guess that sums up what we did. And again, this was in collaboration with the DOST, PNRI, MGB, and University of Tokyo. And again, you may get a copy of our article you can just email us and we'll give you a free copy. So thank you very much for hearing our presentation.
Thank you very much, Dr. Tan. Okay, so we are now open for questions from our participants. Again, I would like to remind all participants that if you want to ask via video, you can ask your questions for just 1 minute. And if you just want to type it on the side, the chat, we will give the questions to the panelists. So, number one, I had a first question here from, let me see, Mr. Brian. The first one I heard is Mr. Brian. Where is the Brian Marfito? Do you have any question, Mr. Brian Marfito? Would you like to use the audio or your video? So
I have a question. So first is um, the iodine 129 and 127. So how do you know where it came from or what type of environment setting using that ratio? Can you expound more?
Okay. Let me answer the question first. So iodine 129, as I've said earlier, so it's the history of iodine 129 is quite well known or studied. Um, a lot of scientists have been using this as a tracer, for example, for ocean currents, for atmospheric circulation. So before the nuclear era, there were a lot of studies as well. So they know that it comes from the atmosphere from cosmic ray reactions. It reacts specifically with xenon in the atmosphere, which produces iodine 129. But again, it is also a fission product. So if there are any fissions happening from uranium or plutonium, you could expect that iodine 129 would be formed. And just how much iodine 129 can be formed can also be estimated by the amount of fission happening. So for example, for the nuclear weapons or the nuclear bombs that were detonated historically, based on the megatons of nuclear bombs detonated, you can estimate how much iodine 129 was released to the environment. And the same with the nuclear reprocessing. The biggest nuclear reprocessing plants are located in the US and in Europe and in Russia. So they have a lot of monitoring programs that monitor the amount of iodine 129 being released to the atmosphere and directly as liquid releases to the ocean. So yeah, also in the nuclear accidents like Chernobyl and Fukushima, there are estimates and measurements that have been done. So we know that iodine 129 comes from these sources through these various studies throughout the years.
hey, thank you, Dr. Bautista. So, Dr. Tan,
Yes.
would like to add something?
No, I think that's pretty much it. So basically, like Doc Angel said, pre-nuclear era, iodine 129 concentration was basically the same throughout the world. And then after man-made intervention happened, that's where we have identifiable signatures from different sources. That's where it actually originated, from man-made sources. That's why we are able to distinguish if it came from the rain, if it came from the river, so on and so forth, because of the previous studies already available. And then our research just made use of the known signatures already and applied it to trace salinity.
Okay, thank you, Dr. Tan. We have another question from Mr. Nedrick Distor. Would you like to use your audio or would you like me to read your question already? So in the chat, okay. So I understand maybe he just want to type it. So I'm gonna read the question of Mr. Nedrick Destor. Okay. Hi, I have one question. I recognize that there is a mixture of undergrad and grad students here. My question is, what are the conventional methods for salinity determination?
All right, so I'll just answer that. So that's what we presented a while ago. That's actually one of the most conventional methods to determine salinity, which is the use of chloride content in water. So if you have high chloride, then immediately you'll say that your groundwater has high salinity. And the traditional methods that we use always say, or more or less assume, that salinity came from seawater intrusion. So with using our method or with further research, we found out that when your groundwater has high chloride content, it might not be as what we previously thought it was, that it came from seawater intrusion. So there are other sources.
Okay, thank you.
So yeah, again, it's usually using chloride content.
Okay, thank you, Dr. Tan. Another question here from Miss Sarah Johnston. So let me read that. Uh, Thanks for the good presentation. The levels of I-129, as I understand, is not at risky levels yet, right? But what would be its health implications if accumulated in significant amount? And what is the set applicable limit for it? Thank you. So,
Okay, so I'll answer that question. So based on the half-life and the concentration of the radionuclides, we can actually calculate the amount of radioactivity or the energy the radionuclide gives. And because iodine-129 has a very long half-life, meaning it decays very slowly, it also gives a very few amount of energy. For example, just for a comparison, the more dangerous isotope of iodine is iodine-131. This is the isotope that is being guarded when they are, or being monitored when there are nuclear accidents. Its half-life is already only just 7 or 8 days. That's how quick it is, and that's how dangerous it is. It gives a lot of energy and radioactivity in a very short span of time. In comparison, iodine 129 is 16 million years. And then, so it's almost stable. So, but yeah, there are some studies that have expressed concern because it's stable. It somehow accumulates in the environment. But what we need to understand is that there are also sinks of iodine 129. So maybe for now, it's not yet a concern. So the sink and the accumulation somehow balances out, but there are studies being conducted with regards to accumulation and the possible risks involved. But for now, I think no alarm yet, no cause for concern. Yeah.
thank you, Dr. Bautista. We have our fourth question coming from Mr. Julius Rafael L. He asked, is this tracing method can be also conducted in wastewaters, such as contaminated creeks and estuaries? And is it dependent from possible contaminations?
Me, okay. So as we've seen in Sunshine's study, there is a distinct signature when it comes to wastewater. Iodine 129 in wastewater. I've not read too much publications about it, but as what we've seen in this study, there seems to be a distinct signature as well in wastewater contaminations. So I think there is also that potential, that possibility that we could use this technique to trace the wastewaters throughout the movement as well. So yeah, that's my answer.
That
Dr.
could be a
Tan,
good further research.
okay. Okay, there's a follow-up question by Mr. Julius Rafael L.
For example, you all right.
Just go ahead, Dr. Tan. Sorry.
No, for example, what he could do for the person that asked, You can get ID 129 signature of the contaminated creek, and then you can actually get water samples from the groundwater that you're interested in to see if there are actually similarities of the signature, if that contamination actually reached the groundwater that he's interested in. That could be a possible, like it's a tracing technique that he could apply.
Okay, so Julius also have a follow-up question. Are there available facilities that are capable of conducting this technique, or there are alternatives?
So I'll answer that question. So currently, what we're doing is that all the sample preparation can be done here in the Philippines, particularly in PNRI. So all the sample preparations we do here, we just send the final product of the sample preparations to Japan for measurement. The problem is accelerator mass spectrometry, as Sunshine showed, it's a very big instrument. It's one whole building, at least the old versions, it's one whole building for one instrument. And it's certainly not cheap to get that kind of equipment. But that is one of the things we are working with. Our group is currently crafting proposals. We're trying to convince our funding agencies to fund to fund our project, that we want to build this facility here in the Philippines. So maybe we could also ask UPLB, SESAM, and the other institutions to collaborate with us to further funding agencies to convince them to build this facility here in the Philippines. But right now, it's not yet here in the Philippines.
Okay, thank you, Dr. Bautista. We have a question here from an anonymous participant. What are the implications or use of these research results to local communities, and how do we communicate these information to non-technical stakeholders?
That's right.
Again, how do we communicate it to local authorities? So basically, it's just telling them that there's other sources of salinity. Because some people, when they know that their seawater, the groundwater is their groundwater well is contaminated with seawater, they immediately close down the well, thinking that because it's actually difficult, once seawater intrudes your groundwater reservoir, it's actually impossible or difficult to actually take out the salinity. So if you actually found out from our research that your salinity comes from, for example, just a pocket of old marine water, probably you could pump out that old water and not close the well per se. So it actually has a big implication on how government agencies would react when someone or there's a classification that there's groundwater salinity problems in the area.
Okay. Thank you, Dr. Tan. We have a question, next question here from Mr. Jason Gabriel Pinza. Can you say that the recharge of groundwater in Pampanga is relatively more recent than 1950?
So I'll answer that question. Actually, that's one of the gaps of our current research right now. So we want to we want to know actually the age of the groundwater. So currently it's being done using tritium or helium tritium age dating. There are different dating techniques. But unfortunately, during the period of Sunshine's dissertation, we didn't have access to those kinds of techniques. But it would be good if we will connect the ID data with very established groundwater age. That way we know if it's really old, if it's new, and that way we would be established more. But so right now it's more conceptual. Right now it's still in the conceptual phase. If it's high, we know that it's above 1950. If it's low, we know it's pre-1950. But again, we want to establish this more by comparing it to established methods and methodologies of groundwater age dating. So it's another aspect for future studies.
Thank you, Dr. Bautista. Here's another question coming from Mr. Brian Marfito. Is there a difference in the results in radionuclide if you get your water sample during summer or rainy season?
Sunshine? Okay, ako na.
Okay.
Okay, I'll answer it.
Go ahead.
So the one caveat of this of our Sunshine's dissertation is yes, it's we only our sampling is only rainy season, and yes, definitely the hydrology would differ between rainy season and dry season. So our conclusions uh, actually only apply during the rainy season. So we cannot say if there are no seawater intrusion during the dry season. So the situation may change the other half of the year. So our conclusions in this paper only applies for the wet season, I think.
Yes, and to add, we also have thematic maps mapping the concentration of iodine 129 in Pampanga. So that could be for your summer season, sorry, for your rainy season. And for future studies, we could also map for the summer season. And finally have a conclusion about the comparison of each season.
Thank you, Dr. Tan. Another question here from another anonymous participant and, and ask, I would like to know more on the analysis of I-129. Is the iodine analyzed as I minus in I think this is in uh, open uh, parenthesis as dash ion close parenthesis or as an molecular iodine in or open and close parenthesis 12, and the question is
I2.
I2, sorry,
Yes.
Okay.
very hard because it's just typed here in
Oo
our
nga.
messenger. Okay, so the question is, what is the chemical identity when AMS is used and when ICT-MS is used?
Okay, so let me answer that. So the sample preparation method for AMS for the iodine analysis is actually very simple. It's only iodine extraction. So we use organic solvent and aqueous solvent, particularly chloroform and NaNO2, sodium nitrite. So we use those reagents, solvent extraction, and we get all the inorganic iodine and we transform it all to I minus iodide. And then the next phase is that we add silver nitrate, silver nitrate, AgNO3, so that all the iodide will be precipitated as silver iodide, AgI. That is a solid, a precipitate. So that AgI we dry, we clean and we dry, and that is the target we put in the AMS, the silver iodide. So it's a solid. For the ICPMS, we don't do much. We usually just if it's very straightforward. We analyze it by ICPMS, and everything that weighs at around 127 mass is analyzed by the ICPMS as iodine 127 for the stable iodine. Yeah.
Okay, thank you, Dr. Bautista. Another one here from an anonymous participant. First, he would like to commend your presentations. You presented well, both Dr. Tan and Dr. Bautista. And the question is, uh, the anonymous participant noticed that the rainwater have higher I-129 versus groundwater. But groundwater is a product of rainfall recharge. Are you saying that I-129 from rainfall is retained in the soil, therefore lowering the I-129 of groundwater?
So I would like to that audience is very observant. So yes, most of the iodine 129 comes right now from the atmosphere and is deposited to the ground as through the rain. The thing again, I said we weren't able to do any age dating. So the rainwater samples we showed earlier, we don't know if it's old rainwater or new rainwater. So we want to confirm that in the future. If it's old water, then it means yeah, it's as it should be. But if it's new it's new rainwater, then it means that some of the iodine 129 gets stuck into the soil, and that it lowers the ratio as it goes down to the groundwater. So these are the gaps. Again, it's some of our results are still in the conceptual phase, but these are the gaps that we want to establish more in future studies. So this Sunshine's work is, I think it's one of the first ones to use iodine 129 in groundwater. So it's very new. So we welcome everyone who are interested to work with us as well.
Okay. Thank you, Dr. Bautista. So we still have plenty of questions here in our list.
Wow.
Yeah. But we can accommodate only what I maybe 3 left because it's already 2:57. We need to finish this in what 3 o'clock. I would like to also ask the CET if we can still add more questions because I can see here in the sidebar that we still have plenty of questions. But maybe wait, we have still one question. Maybe we can accommodate this one from Miss Leonila Sikat. You said GW samples were taken from production wells and shallow wells. Do you mean wells from water district? What is the depth of the wells with high salinity and the piezometric level? For shallow wells, what are the depths and salinity? Can you show a map of this? Thank you.
I think we have that covered in our written literature, but I can say that there are shallow wells that was traced to have high salinity, and such as deep wells also traced with high salinity. For deep wells, the depth it was taken was around 100 to 200 meters from the surface level. And then for shallow wells, it's 20 meters below. So that's our local pozo, wherein we took samples as well. So we found out that the ones who had who had high salinity due to evaporated water is actually less than 500 meters away from local fish ponds and rivers. So you could just imagine that it might have been contaminated from those water sources. And to add, actually, what's actually difficult in our country is that our groundwater wells has actually a lot of perforated holes in different depths to actually maximize commercial purposes. So one scientist actually said that it's actually difficult to have an idea of the age of our groundwater because we have different levels open in our groundwater. So even if you say that the groundwater well is 200 meters deep, the water sample probably that you get, because you have many holes at different levels, is an average of that depth. So that's one thing we want to actually take a look at. But based on our research, we could say that those deep groundwater wells are actually has an effect because of the location with regards to near surface water.
Okay. Thank you, Dr. Tan. So we have still plenty of questions right now from our participants, but may we request you to send us your email. You can email us your questions because we are really out of time right now. Again, thank you very much, Dr. Tan and Dr. Bautista.
Thank you
Thank
so
you very
much.
much for. You
Today
can
we
answer
need
all the other questions via email if
Thank
they
you so
want. So
much
you
for
could
your
just send
questions
them all.
also.
Yeah.
thank you very much
Thank you for your interest in our
the
work.
questions. So for the closing remarks, may I call in Forester Sophie Alira for any announcements also? Tita Sophie, are you there already? While waiting for Tita Sophie, so again, thank you Dr. Tan and Dr. Bautista. Yung names nyo ang kailangan namin eh. Sunshine and Angel. Today, yun ang kailangan namin.
Yes.
Sunshine and Angel to light us up and Angel to guide us. So ayan na si Tita Sophie. Are you ready, Tita Sophie?
So good afternoon. On behalf of the School of Environmental Science and Management, we would like to thank our great speakers, Dr. Sunshine Tan and Dr. Angel Bautista, for the new insights, new learnings, at very interesting research study result, as stated by our participants, by our 154 participants. And of course, to our participants who joined us today, amidst the COVID crisis, kahit nakakulong tayo, pwede pala tayong lumabas, pwede pala tayong makinig, kaya pala, kayang-kaya pala natin. Maraming salamat sa inyong lahat. So again, we are inviting you to join us on May 29, 2020 for another seminar series. This is actually our second seminar series with Dr. Neil Tangilut from Pampanga State Agricultural University. He will talk about biosecurity, the key to the control and prevention of African swine fever. We will post the details of the topic of the lecture on our website before the date of the seminar through our CET active members, Jessa Aquino, Patrick Cabangbang, and Cherry C. Padilla. So thank you very much at hanggang sa muli nating pagdinig, pagkikita, and stay safe everyone. Salamat sa inyong lahat, sa inyong pakikinig.
Thank you very much. See you again in our future Living Dangerously seminar.